Let's go. Welcome to the AI Engineering Bootcamp, Cohort 5, Session 18. We're talking inference optimization. We're kicking off Hack Week this week. Everybody's building, shipping, and sharing. I had some great discussions in office hours today. Folks showing me their demos, telling me about the features that they're trying to cram in. Lots of great stuff happening. You guys have done a great job submitting your projects, and there's just so much to look forward to this week. It's the best. Okay. Building, shipping, and sharing around the cohort. Shout out to Richard Moss getting out there and sharing about the last few weeks, how he's been building Chief Joy Officer, getting out ahead of the curve here. Richard, way to go. So love seeing this. Now, I also want to just encourage everybody, like right now, just go get on LinkedIn and just spam it with some reposts of this. We got to get this in front of people. What do we got? 51 other attendees? That's it? We can do better than that, guys. Come on. Let's get some reposts. Let's get some attendees. Look at this. Mike C. You see how easy this is? Literally, he just copied and pasted like an absolute legend, the copy right there. Look at this. Todd LLM. What did he do? Oh, he even added a little something to it. Just a repost. That's it. We're making it easy for you guys to build, ship, and share. Also, like, I just want to give a shout out to a guy none of us have met yet, but he's going to be joining us for cohort 6. Okay. And I just want to point this out because obviously Mark is trying to get after it here. He just finished the AI Engineering Bootcamp Challenge. And we've added a fine tuning layer to it, as you guys know. And he is just rip roaring, ready to go. Now, please note, you know way more than Mark. He's sharing like a legend on just the challenge. Imagine how much content you actually have that you could start sharing today with your network. It starts this week, and I really look forward to seeing what you guys build, ship, and share coming up. All right, we've got some homework coming back to you guys. The deep research homework. Number 14, 32 submissions. Look at that. How many 100%? Wow. What is going on there, Tyler? What's going on there?
Huh. So the biggest thing was that on one hand there wasn't any major questions. Everyone did a great job keeping their video concise. I'd say that especially compared to the last homework I graded, there was a vast improvement in everyone's presentation ability, which, very heartening to see going into demo week. So great job everyone there. Yeah, everyone just crushed it on the assignment. And overall there wasn't as many questions to get, nuanced hung up on, but
Yeah.
overall, great job.
All right, we'll have to make it
Perfect
harder
scores.
next time. Thanks, Tyler. Awesome. You guys are crushing it too hard now. Great lessons learned. Deep research is not anything new necessarily. It's simply a combination of key concepts. See, oh, that's a banger thing to say in an interview right there. You see, deep research isn't actually new. Let me tell you why. You don't need to pay $200 a month. This is real value you can bring to people. Reflection versus reflection. I like that one as well. How to avoid rate limiting, still haven't learned it. Evaluating multi-agent systems, yes, nobody knows how to do this yet. You guys are out on the edge. Optimization strategies, dealing with latency in production. All you guys getting out there sharing, fantastic work. Keep it up. Couple shout outs, Ben, Kenny, obviously, you guys killing it, still out there. Krishanu, Lewis, continuing to kill it. Okay, continuing to kill it. Now, I wanna kind of tell you a little bit about what to expect this week as we head into the real build, ship, share artifacts that we've been working up towards for 10 weeks. So essentially, we kick off what we like to call Hack Week here. And what I want to point out is that you guys basically have support, coverage, assistance live every day from now until demo day. Now, there's one day that we don't have any live sessions, but we want you guys to get into the lounge and start building. Shout out to Frickster, aka Dirk. Saw you in there today crushing it. I think now is the absolute best time in the world to really start behaving like a community. If you want to start making connections, if networking is something that you want to start doing, you can do virtual networking directly in the AI Makerspace Discord. Whenever you're working on something, just hang out in the lounge. This isn't the public lounge. This is just for our cohort. And if somebody comes in, maybe you can tell them what you're working on. Maybe you can talk about some bottleneck you have. In fact, that's exactly what I want you to think about right now. And again, I'm going to ask you to do something. Don't forget to repost that thing on LinkedIn, demo day. Also, I heard from folks in office hours today, like, oh, I'm trying to add this feature. I just had it working, but now I'm running into, I can't stream images to my app. Now I'm running into, I can't add this final piece, and it just broke everything. And, many of these folks are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 features deep. Do you need 10 features for demo day? Of course not. But a lot of you guys perhaps have solved the same problems, but you just don't have line of sight into the problem space that others are dealing with. We're seeing a lot of folks working solo on these projects, and I want to really encourage you guys to jump into the general channel now. If you have a bottleneck that you're struggling with, tell us about it. Tell the cohort about it. Tell the community about it, okay? And again, we want to see you guys in the Discord on Saturday. We've all got kind of a busy week where many of us are traveling this weekend. Wiz, of course, is going to be present at the GTC conference, which is a big one for NVIDIA. I know some of you in the cohort are also going to that. So if you do, make sure you get a pic with Wiz while you're there. But this is kind of a busy week for the industry in general. And I want those of you that are sitting there working on Saturday, you have an interest in building community out in the future, get in there and, show some peer support, show some leadership, show kind of the model of what you would like to see from people that are supporting your projects. This is an opportunity for folks that want to get out there and get after it. And this is something that we can use to help identify people that we can elevate into positions in the future. So Saturday, get after it, hack, chill in the lounge. Otherwise, you can always hit up your peer supporters outside of these dedicated hours. You can always hit up me or the Wiz. And you can always lean on your journey groups as well. Don't hesitate to reach out to folks. They peer supported you this far. They will continue to peer support you through demo day. Look at how many amazing projects we have teed up for this cohort, guys. This is crazy awesome. Okay, it's awesome. And I want to make sure that you guys kind of have everything you need. So let us know if you don't. We've started to put together a run of show here. This is something that we're going to start marketing. So you can actually see this publicly now. It's something that we haven't shared quite yet, but look at this. We've got room 1 full. We've got room 2 full. We've got room 3 full, guys. And we have to actually add a 4th room because you guys are crushing it so hard. I know not all of you have probably even submitted yet. So please get your submissions in by the end of the night tonight, so we can really make sure we know exactly how many presentations. And as we continue on here, what we're going to do is on Saturday, we're going to send this out to our entire audience. And we're going to, yes, AIE5, that's correct. I've been in between cohorts in my thinking. I think perhaps that was a faux pas on my part. But we're going to send this out to our audience. And, you're going to get your ideas, information out in front of tens of thousands of people across the newsletter, across LinkedIn, across Twitter. Uh, this is a sizable audience. This is a huge opportunity for you guys, and I want you to make sure that you're getting out in front of it. We're going to announce the rest of the judges on Tuesday, but here's just a couple that will be there that, these are the kinds of audiences you can easily get access to if you bring it, if you impress these people, if you do something memorable that they want to tell their friends about. This is the power of networking. Okay. A lot of fun stuff. And really, it's going to be awesome. It's going to be a great week. Don't forget, you can always join us Monday, first thing in the morning, in the lounge for some accountability. If you really want to be held accountable for demo day somehow, I want to stop working on features by Tuesday during rehearsal. Come on into the lounge and then make sure you come back the next Monday after you finish demo day so we can say, hey, did you do it? Did you do the thing? Next week, what we'll be talking about on Wednesday is we'll be going through all of the awesome launches that DeepSeek put out there for open source week. There was a whole bunch of libraries that they just straight open sourced. And these are very, very powerful libraries for lots of different things that help something like DeepSeek R1 run efficiently and at scale. So this will be really, really cool. It'll be kind of a whirlwind tour. Join us for that. And then finally, last class, you guys liked a lot of it. Breakout room's good. Presenters kind of got stuck. Great session. Felt good because we had time to do it. I've been anticipating local model hosting this whole time, and all it took was 2 or 3 commands. I think that's a good piece of feedback. Overall, great sesh. So you guys are literally just picking these things up super quick. Suggestions. Well, yes, this is the most challenging homework of all. Wish we had had more time for the walkthrough. More time, of course. I love this feedback. Thank you for this feedback. This is the kind of business value proposition that I think is so important. And I think sometimes we don't focus on enough. And, a lot of people are telling me after we focus on all this engineering, it'd be nice to focus a little bit more on the business somewhat. And I think this really helps us guide how I can adapt the curriculum slightly for AIE 6, but also things that we should potentially build in the future. This is really useful stuff. So thank you for that. And then additionally, we've got got it working, et cetera, et cetera. Waiting on the endpoints turned a 5 out of 5 into a 3 out of 5. Oh, what a shame. We're going to get you 2 breakout rooms today because we've got some models to set up. Okay. With that, here we are. We've been through a lot together. This meme should start to be making sense to you guys, and you should start to be feeling a lot of this. All of this new stuff needs to be fit into the real world and all the stuff that hasn't gone away. We are at inference optimization, and that's what it's time to talk about. We want to sort of review the fundamentals of quantization so we can really understand inference optimization today. We want to understand specifically how we can kind of speed up inference. We're going to focus on 2 very popular, one more of a best practice these days than the other, but one, the OG methods for speeding up inference. We're also going to give you a little bit of a sneak peek into one of the more edge methods that hasn't really caught on, but is quite cool. And we're just going to do it with the classic Llama 3.18 B-Instruct. It's still one of the golden open source models that you can pull off the shelf. And then we're going to remind you guys what you need to prepare for rehearsals for Tuesday. Make sure we have time at the end for that. So let's talk about quantization and all the cues, and then we'll see how fast do these things really make the LLMs go burr. How much faster? Is it really worth it? We'll talk also about dollars and cents. What should you be choosing in a production environment today? Okay, so when we think about inference optimization, we want to remember the stuff we talked about last time when we started talking about on-prem. We want to remember that LLMs, chat and embedding models, they run on GPUs. And we need the compute, but we also need the memory. We want to remember that we're talking about inference. We need GPUs for a lot of stuff, but this is for inference. This is like the model's done. Lock it in. Lock it in. I'm not changing it. I just want to do inference. And so we might call this post-training quantization. You might see this as sort of a keyword. So I'm done training. I'm done doing everything I need to do. I just want the output of a single inference to be the same, roughly, as the old output from a single inference. But I want it to be faster. And the way that I make it faster is I focus on the stuff that matters the most, and I sort of don't worry about the stuff that doesn't matter so much. And we can use quantization to accomplish this. Question, which weights in an LLM contribute to inference the most? Of course, it matters. What do you mean by inference? What are you aiming at? What task are you actually doing? What next token prediction are you actually applying to a use case? But in the end, not all of them. That's for sure. And in fact, a fun fact is that, and we've learned this from extreme quantization, is that the most common model weight is actually 0. So it's not, if it wasn't clear that everything doesn't matter the same amount, that does really make it clear. And when you get to the extreme quantization, you start to see, wow, because if you go super extreme, you just have 1 or 0. You start to see that most weights really don't matter that much. In other words, some weights contribute more than others. That has implications for inference. And so when we talk about making this stuff go faster, we're talking about flowing the sequence through the network so we can predict the next token. We're talking about flowing faster through the network. And, what quantization does is it lets us sort of squish the weights that matter the most while we kind of just eliminate the weights that don't matter at all. And we have this fundamental trade-off here. We can squish everything, but we also want to keep important stuff. So if we make everything too small, we might actually get rid of some of the important stuff. And we don't want to do that exactly. We want to find the trade-off. And this is the goal, especially if you're operating at scale and every LLM call really matters, you know? Okay, well, how do we do it? Well, I mean, the first thing is you want to really understand quantization. And I think we did it. And if you can just do it, maybe that's enough. But this idea is like, what we're doing is that we want to represent all these billions of weights very efficiently. We want to compress them. LLMs are compression algorithms. We feed a huge sequence in and we plop out one token. And then we do it again. And like there is a loss of information anytime you do a compression, right? If you look at images, it's very easy to see this. With words, it's less easy to see. It's even easier to see perhaps if you look at like literally the numbers themselves. And you can think about FP32 versus FP16, and you can think about these different data representations with different amounts of precision. If you have less precision, you're using less bits. And, the different data types, right? If you watched our Pydantic AI event recently, we talked about Python type hints. And this idea that, like, it really matters what the type is especially when we're building in production and we need to do validation and we need to make sure this is going to plug in directly to that function and that API call is going to get what it needs to give me back the proper response, etc. So it's all sort of connected that we need to understand what the data structures are that we are using and what the optimal ones are to use. And if we have less bits, we're going to be less precise, vice versa. So these off-the-shelf data types, they have built-in ranges of precision. And so when we switch between them, one question is when we lose the information, like, can we go back to the original representation? You think of like principal component analysis from back in the day. And the answer is, well, kind of, but also no. But yes, like it's fine as long as we didn't quantize it too much. This is what's called dequantization. We talked about this with Q-LoRa training. We would quantize and dequantize. And this idea of dequantization, we need this kind of quantization constant. Remember, we were quantizing the quantization constant last time when we were doing the fine tuning? Well, this is what that's related to. That constant, it really helps us to understand what's going on and how much information is lost when we quantize. So some info is, of course, lost when we go from a 32-bit representation to like an 8-bit representation. And then when we go back to a 32-bit representation, we can go back, but it's not exactly perfectly the same, of course, right? It's like the classic sig figs problem. And the amount that is different, the amount that we lose, that's what's called the quantization error. And it's this quantization error that is sort of the crux of some of the methods that we're going to look at. We really want to focus on this, and we want to really make sure that this is kind of minimized. If we can minimize this error, think of it as sort of a loss function, and we're sort of trying to optimize towards it, then we can actually have a really, really robust quantization method. Of course, if you don't ever care about dequantizing, then maybe you don't have to even worry about it. And that just means you're fully locked in and you can't go back. So again, trade-offs. Now, we talked last time when we did a notebook that had quantization, we talked about for each block, we talked about k-bit block-wise quantization. And what happens is if you imagine that these are 32-bit and we're going down to like a 4-bit representation, what we do is we calculate this sort of error. We calculate the average of the standard deviation of the errors for each quantization bin or block. And this blockwise quantization introduced in the paper that preceded LoRa by the same author is just exactly what that image showed. That's sort of a great visualization of this blockwise quantization. And, it's a great article altogether about the basics of quantization. And so the big idea is that we got to discretize and we got to discretize more. We got to make it more discrete, more blocky, less resolution, less precision. But we want to get just enough that we can hold enough information so that our output is good. And so we're going to look at a few methods to do this. We're going to look at a few methods that do sort of smarter and smarter quantization. And we're going to talk about what the best practice one is. We're going to learn which one to pick, basically, today, and what to look out for in the future. But of course, if we're going to do this, we need to get all these model weights. And we need to set up some scalable, open, and private endpoints. And we're not going to do it in a single breakout room. We're going to give you 2 breakout rooms. So let's play with quantization after we get some models with different quantized versions down onto our machines. So I want to go ahead and go to Wiz now to show you how to set up endpoints that we'll do in the first breakout room before we come back and we discuss what the techniques are doing under the hood. Wiz, over to you.
Oh yeah. Okay, so basically what we're doing is we're going to set up 3 inference endpoints that are going to power us through the day. So I'll go to Hugging Face and we will look at this together. Whoop. All right, we're going to go to our inference endpoints here. And the idea is we're going to need 3 of these things. So I've got them all set up here, and we'll go through how to set up the first one. There are effectively 3 models that we're going to use today. This is because in our actual notebook, you'll see that we're going to do, 3 different inference endpoints. So you can do this one of 2 ways. I'm going to show you the hard way, and then you can go ahead and use the easy way, which I'll also show you. So let's just grab this, GPTQ int4. Don't worry too much about what that is. We'll talk about it, in detail after we get these bad boys set up. But so let's go to our endpoints. What we're going to do is we're going to click plus. To create a new inference endpoint, we're going to paste that in so we can select our model. We're going to give it whatever name we want, cool name for model. And then we're going to select a GPU. We can get away with the T4, or you can use the L4. I'm going to use the L4 just because. And then in our container configuration, we don't got to do anything. In our environment variables, we don't got to do anything. For our security level, we're going to leave it as protected, and we can just click the create endpoint button. That's it. Now, that was the hard way. Okay, let's talk about what the easy way is now. So if we want to deploy these as endpoints, we can click on the link to go to Hugging Face, right? And then we can click the deploy dropdown, and then we can click the HF inference endpoints button. And then you'll notice we're already at this screen. The model's already been filled in. We can name it whatever we want, of course, a cooler model name. And then, again, we want to select the hardware for this model, which is going to be the L4. You can use, again, the T4, but it's going to be a little bit slower. The L4, there you go, boom. And then we hit create endpoint, right? So we can actually deploy these checkpoints right from their checkpoint. Now, it gets even easier for Meta Llama. We click on the endpoint, we go deploy, we go again to HF inference endpoints, boom, and then you'll notice it comes with an optimized configuration, right? Very cool. So let's call this thing B&B Llama, right? We do have to you'll notice we don't have to choose the hardware here. We're not choosing the hardware, right? It already knows. It's already picked it for us. But we do want to make one change, and that's in our container configuration. We want to change quantization to bits and bytes, right? This is so that it is quantized. If we don't select this button, we're using the unquantized version of the model, just the normal version, which is going to be slower, right? So spoiler alert, bits and bytes is going to maybe not do so hot, okay? But it'll do even worse if we don't remember to select this quantization option. Very straightforward. The thing that this is going to take is your time. So what we're going to do in the first part of the notebook, and you'll notice we got a lot of pip warnings, okay? But you can safely ignore them. First of all, we're going to download some code that we need, easy peasy. Then we have our actual HF token, our notebook login, and then we have bits bytes versus GPTQ versus AWQ. It's the whole thing. You can see it here. We're gonna pip install this cell. So what you need to do in the first breakout room is you need to get to where you can click this button, because it's gonna take a very long time. Okay. Once you have clicked this button, you're safe to move on to spinning up those endpoints, and it will complete before we enter our second breakout room. But what we're going to do in the first breakout room is basically get to the point where we can run this pip install, and then in parallel, we're going to set up these 3 inference endpoints. This is a welcome to real life. We need to spin things up. Spinning things up takes time. Okay, that's that. basically all we're doing is set up for the second actual meet breakout room where we're going to pit these things against each other. But for this one, again, just work your way through the notebook until you get this cell running. It's going to take a long time. But we're gonna have go back to Greg and hear all about these methods in the interim, and then we're gonna get our inference endpoints spinning up. One thing to kind of like one bonus tip if you want it, right, is that you might want to change auto scaling to after 1 hour with no activity, because the endpoints might spin down between when they first come up and then when you get into breakout rooms for the second time. If you're worried about costs and you just want to leave it at 50 minutes, that's totally fine. You can either periodically spam them with a request, or you can just click there'll be a button if they spin down that you can press that will quickly spin them back up. It will still take time, but it'll be much less time than if you're setting it up the first time. But I would suggest moving this to after 1 hour with activity. This is going to be the most pleasant experience for you, though you will pay for this 1 hour versus just the 15 minutes, as the endpoints will go to sleep between when you finish loading them and when we leverage them in the breakout room. All right, that's that. First breakout room, just a bunch of setup. Set it up. There you go.
Set it up, so we can knock it down. Remember, quantization. It's just rounding, bro. All right, 10 minutes. Let's do 10 minutes. And just get these things rocking. Chat about quantization. And the other thing that I'll sort of recommend, if you guys like already have this done, like some of you absolute legends out there, then I would highly recommend that you take a look at. Let me find the link from the slides here. The visualization of quantization paper. It's in the extra go deeper on session 18 thing. Let me pull it up here for a second. If you already have these spun up, and then chat about what exactly is going on in blockwise quantization, if you don't quite understand it, or see if other folks in your room, this is an opportunity to give first if this is something that you're particularly good at already. This visual guide to quantization is what I'm talking about here. All right, so 10 minutes. We'll be right back, and then we'll keep the discussion rolling. GPTQ, AWQ, VPTQ. We just need the endpoints. We'll see you back in 10. Have fun, everybody. Into it. Back from breakouts. Let's get on with the show. First, I'd like to introduce you to GPTQ. Guess what it stands for? Classic. October 2022. This was one of the earlier ones. Generative Pre-trained Transformer Quantization. What a brilliant naming scheme. Hey, look, due to their massive size, even inference for large, highly accurate GPT models may require multiple performant GPUs. There's emerging work to relieve this pressure via model compression. We can read these papers now, and they make so much sense, right? In this paper, we address this challenge. We propose GPTQ, a new one-shot weight quantization method based on approximate second-order information. One shot based on second-order info. Our method more than doubles the compression gains relative to previously proposed one-shot quantization methods. Hype. The paper goes on to say, to date, only basic variants of round to nearest quantization have been applied at scale. While this work works well for low compression targets, for instance, 8-bit weights. While this works well for low compression targets, 8-bit weights, they fail to preserve accuracy at higher rates. Got to read that at the right. Yeah, okay, so this works well down to like 8-bit, all right? It doesn't work well below 8-bit. In this paper, we present a new method, which is efficient and precise enough to deal with hundreds of billions of parameters and get down past 8-bit to 3 or 4 bits. That sounds pretty good. Further, we show that if we can get into the extreme quantization regime, talking about that 2 bits, remember 1 bit is just 1 0, right? I mean, it's like 2 bits ain't that much information. You know, and the same authors of that visualization of quantization little article here, GPTQ is arguably one of the most well-known methods used in practice for quantization down to 4 bits. This is from Jay Alamar. He did the Illustrated Transformer, and Martin Grutendorst. This is the OG, GPTQ. And you'll notice this kind of language around all the tooling that we've kind of looked at. This is from Olama. Hey, look at this. By default, Olama uses 4-bit quantization. So surprising to see, really. Okay, so how does it work exactly? Well, GPTQ basically goes in and they look at each layer. They process each layer independently and in sequence. And what they do is they look at each layer, and they essentially look at the second order information, or they look at the gradient of the gradient. They look at the derivative of the derivative. And so like this idea of like looking at the sensitivity of how the model's output changes when we change the weights. We actually talked about this yesterday during our optimization session. If we look at sort of D change in model, D change in weights, we can kind of think about this as just using derivative information, but it's using a second order information. That means it's the second derivative. That's this inverse Hessian, for those of you that may have studied this kind of matrix algebra deep in the tank in grad school. And this is one key aspect of it. We're literally just looking and we're calculating, hey, when I change the output, how much do the weights change? Now, of course, what output are you looking at? Which weights are you looking at? These are important questions, but this is sort of a method that kind of works, you know, specifically where we tell it we want it to work, just like all of these methods. And the 0-point quantization is basically focusing on how we're doing the quantization and how the quantization error is really, you know, affecting the output in the end. So if we kind of 0-point things, what we're doing is we're actually doing this kind of putting the 0 points so that it's asymmetric, so that it's not quite, you know, it's 0 in FP32 is not the same as 0 in int8. So we don't actually align the zeros here. We don't really care about aligning the zeros in an asymmetric quantization. When we do a symmetric quantization, we do care about aligning the zeros. Now, does that manifest in sort of changes, again, with sensitivity in mind of the output? It's like, well, you know, maybe, maybe not. And it's not just these two methods. Every time you have one of these papers, and this is really important, we're not going to go into the details. There's this sort of asterisk other optimizations too. There's things that are down closer to the GPU level. The little GPU programs, the kernels, where they're essentially looking at the way the calculations are done, the literal matrix multiplications, and they're finding ways to actually make them more efficient. This is something that, again, folks like Daniel and Michael from Unsloth are doing all the time. This is like if you want to get into CUDA and sort of programming down at the GPU level, all of the researchers that come up with new quantization techniques are interested in this stuff, and they do what are so-called micro optimizations down at the GPU layer. So again, look out for these in all these papers. We're not going to go into each and every one of them. That's beyond the scope. Moving on to a newer, more best practice model that has improved on GPTQ, we look at AWQ. And so what we want to think about is actually A stands for activation. After training, what we have is we have activation information that indicate which weights are the most important, like which weights are activated given a certain input as I'm doing inference toward a certain output. And it turns out that if we think about the activations, we can think about them in the same way as like the quantization constant. We can quantize what we quantize, and we can quantize some more. And we can quantize the weights just as we can quantize the activations. And so like this is sort of the key insight here. If we look at the paper, what we can read is we can read that AWQ finds that, hey, look, not all the weights are equally important. Protecting only 1% of salient weights can greatly reduce quantization error. To identify the weights that matter, salient weight, these channels, we should refer to the activation distribution, not the weights. You can't tell by looking at the weight numbers if they matter or not, but you can tell by looking at the activation numbers. To avoid the hardware inefficient mixed precision quantization, we mathematically derive that scaling up the salient channels can reduce the quantization error. Okay, so we're going to try to get a handle on what that's saying. But the big idea here is the activations tell the story. The activations lead the way. Hey, that thing activated. Let me make sure that I keep that one. And so the closest work to this, as they said in the paper, GPTQ, this is basically 7 months later, June 2023. 2 steps. They do a weight only quantization, right? And then they do an automatic reduction of quantization errors using, they do an automatic reduction of quantization errors using activation information, activation aware weight quantization, AWQ. So they do this sort of so-called on the fly weight dequantization. So they're basically figuring out which ones matter, determining the weights that matter by looking at the activations. And then they're keeping the ones that are really like, oh man, those some chonky activations. Let's keep those in higher precision. But then they have this mixed precision problem that they have to solve. And so what they do is they essentially do kind of what all the other papers do. They do these micro optimizations, they do these little GPU programs, they do these kernel fusions, and they also are able to speed it up. And they don't just do that, they do, again, other optimizations too. But the big idea is we've got the weight only, now we use the activations. And, really like what we've seen is that when we think about which one we should choose, AWQ has sort of risen as the gold standard here. So like Wiz, I believe we set up our original inference endpoints with AWQ. Is that right? Or at least when we set them up and we see AWQ, we should kind of think probably that one today, more or less. How do you think about this?
Yeah, so basically the way that I would think about it is just as you said, right? So the idea is it's whatever it says. So if it says AWQ, then it's using AWQ. If it doesn't say AWQ, then it's not using AWQ. Whenever we use a checkpoint, especially in today's day and age, it's going to tell you what kind of checkpoint that it is. And so we're going to focus on things that specifically say or explicitly call out, AWQ. It's just like the standard across the board. Now, if you're using different hardware, etc., this might be different, but we're not going to broach that. If you're using a GPU, which is the recommendation, AWQ is going to be the one that you're looking for.
And just so I'm clear, like we're quantizing the weights now. We're quantizing the quantization constants that we use for dequantization, and we're quantizing the activations. We're like just quantizing the heck out of everything. Do we expect to quantize even more stuff in the future? I mean, it feels like that's kind of the name of the game here. What do we quantize and how much?
We're gonna, yeah. So we'll quantize anything. We'll quantize the whole thing. We
And
even
when we
found
get
ways.
quantum computers, I mean, we're just going to quantize even further, right?
Correct. We quantize everything. Uh, Everything all the time. So we're even quantizing the KV cache these days. You know, we're
Yeah.
if it's represented by a number, we're gonna definitely try and make that number smaller than it needs to be. Or
Yeah.
sorry, as small as it can be, without
Mm.
sacrificing perf.
That's right. That's right. We want that perf. And yeah, so if we're doing compute-er stuff, maybe there's some quantization happening so we can get more juice for the squeeze. Okay, good stuff. We got one more quantization method to cover, and this one is in the one we talked about, the extreme quantization regime, which is quite interesting these days to follow. People are doing crazy stuff. September 2024, VPTQ comes out. This was work done at Microsoft. A traditional scalar-based weight quantization struggles to achieve extreme low bit, due to the redundancy in LLM weights, they say. So, not only are they not that important, they're even redundant. We got to get rid of them. What this one is doing is it's basically using what's called a code book. It's using a lookup table, and this sort of allows us to be kind of really effective at compression. It allows us to kind of reduce the storage requirements. And, remember kind of we talked about compute and memory. Well, this is kind of like to that end where we've got this lookup table where we've kind of indexed the important information that we need to kind of like go, because when we go to super extreme bit quantization, we're losing a lot of information. So, we've got to keep in mind that when we quantize, we dequantize. And when we kind of keep a lookup table on hand, we can do things a little bit more efficiently. So this VPTQ method has this very low dequantization overhead and allows us to sort of, go back very efficiently to a higher precision, like you would expect you need in an extreme quantization regime. And this is sort of the magic of these code books. And this is the vector in VPTQ. And kind of, the kickoff of their paper, they sort of cover a number of these different methods. And I encourage you guys to look into all of them. And what we're seeing is more and more people pick up this sort of vector quantization, this sort of VQ, and sort of apply it to different techniques. Now, I want to just pause here because I even see here was GPT VQ, where they sort of applied vectors to GPTQ here. What's going on here at the edge before we get into the demo, where people are thinking about vectors and people are thinking about the extreme quantization regime? What do we expect to happen? Is this really going to be something that's production ready, really ever? What's your take on this?
Yeah, so we have there's always innovation in this space, and that's important. And it's something that we continue to be excited by, let's say, right? But things like VPTQ and other inference methods, such like this, not always necessarily uh long lasting, let's say, right? So a method like VPTQ is dope, but it doesn't really fit well with the existing landscape, right? So a lot of these a lot of these methods that you're going to see come up and come out and gain some traction initially, you know, not all of them can live forever, basically, right? They've all got to pass the time. The idea is that something like VPTQ is dope, just waiting for its time in the sun to showcase where it's really extraordinarily effective. Yep.
Yeah, and just to be clear about this, I mean, when we talk about extreme low bit and 2-bit, basically like there's kind of like 4 different numbers that a weight could be, and that's it, right? It could be like 0, 1, 2, or 3, or however you want to talk about the 4 different numbers, you know, 0, 0, 1, 1, 0, 1, 1, 0. But like that's it. Like all the weights in the LLM are just one of those at that point. And then we're seeing that we still get decent answers sometimes. Is that right?
So yeah, so yes, so but with the caveat, right? That you know, 2 bits, as you let us know, right? Represent certain combinations of binary, right? So you know, we got a 0 0 1 0 0 1 1 1, right? So 4 states, and we don't actually use those as our number. It's not like the number is 0, 1, 2, and 3. It's more like those bits map to constants that represent some kind of weight that is expressed as like a delta from some mean, right? So like we already talked about bits and bytes, right, which has its 4-bit quantization. Well, really, it's 4 bits to map to a certain point on a normal distribution about a specific mean, right? So these quantization strategies can go so extreme because we can rely on our good old friends' stats, right,
Yeah.
to carry us over the finish line and say, well, if most weights in a model are normally distributed, our most, you know, if most of our model weights occur very close to, you know, say 1 standard deviation away from the mean, or 1 standard deviation the other side, right? Then why we need all these bits, bro? You know, just
Yeah, yeah,
bucket
yeah.
them. That's good enough. Yeah.
Well, like, so can we think about this as like those 4 states are like 4 features to sort of put it back in sort of a machine learning sort of conceptual context? Can we think of it as they've been identified as sort of the 4 most important features in the network, and we're just using those now?
Uh, I hadn't thought about it like that, but yes, I agree with the
Okay.
words that you just said. Yeah,
Okay.
for
Yeah, yeah, yeah.
sure.
Okay.
Yes.
All right. Okay, yeah, because that kind of makes sense instead of like,
Yes.
it's all 0 or 1. Okay, all right. Good. Okay. Then we're gonna go into inference by comparison. Since you guys already had a quick breakout room, um, what do you guys think? Do you guys want to take a break right now, or do you guys want to keep rolling? What do you think? Thumbs up if you want to take a break right now. Derek, you're on your own, bud. You're on your own. Okay. All right, let's keep rolling then. Let's keep rolling. So let's get into the demo. What we're gonna do is we're gonna do Meta Llama 3.18b instruct, and then we're gonna compare it. We're gonna compare it with a couple different specific metrics. We've talked about some of these when we've looked at LangGraph, when we looked at LangSmith, when we looked at the back end, we talked to LLMOps. Whatever it is, your actual thing is you want to look at, and this will be in the meta comparison one. We've got sort of 2 notebooks for you today. But to get GPTQ, we're actually going to use this cool GPTQ model repo, and it's actually easier than the original thing that they released with the paper because it's been better maintained. And in a similar way, we're going to use the auto AWQ repo to use AWQ. So with that, let's go ahead and just get into the demo now. We'll take a quick break just for you, Dirk, right before breakout rooms. Okay, just a quick break, right? All right, over to you, Wiz.
All right, so we're gonna look at 2 notebooks really quick. One notebook is kind of like the one that we're gonna focus on, and then the other one is just a sweet bonus notebook. Okay, so first things first, You've already installed this. If you're seeing large walls of red and you're getting scared, just ignore the large walls of red. We're working in Colab, which comes with a bunch of things pre-installed in the environment. We're trying to install things that it hates, and so it's gonna complain, but it doesn't matter because it's gonna work. Okay. Then we're going to spin up these inference endpoints, which you should have already done. And then we are going to look at our giant wall of strings. This wall of strings means nothing. It's just so that we have 100 strings to do generation with. And you might say, well, why isn't just every single one of them like keep your friends close, but your enemies closer? A terrible one to have just jumped to. But it's because there is some intelligent caching that occurs on Hugging Face's side. And so if we use the same string over and over again, we run the risk of hitting cache, which is going to make us think that they're all the same. They're all in same, of same import. Okay. Then we're going to create this inference helper function. All it's going to do is it's going to measure the endpoint performance by smashing it with requests, and it's going to do them one by one, like true lad status. So we're gonna feel the inference speed ups in our bones today. But the idea is that we're just going to see how long it takes for requests to complete, for tokens to come back, and we're going to collect this information so that we can measure the things we care about. Now, the things we care about are time to first token, and these are like things that we care about in real life. This isn't like some stuff that we'll never care about again. This is like straight up time to first token, very important. How long do we got to wait before the thing starts talking to us, right? If this is too high, it will feel bad, even if the generation is lightning fast, right? And the logical extreme of this is where we don't wait or we don't use a streaming output, right? We wait for the whole response to be generated, and then we get it all at once, right? Simultaneously. People, when they have that experience, become upset because it feels slow, it feels bad, and so time to first token is important. Then we have inter-token latency. Inter-token latency is just saying how long between each token. We want this to be low. The reason we want this to be low is because we want the LLM to crap out tokens faster than we can read the tokens. There you go. And then tokens per second. I mean, it's a function of these other two, but the idea is how many tokens per second over the course of the generation. Tokens per second is mediumly useful, right? These two are very useful. Tokens per second is a vanity metric. Let's call it. Okay. When we look at the helper function here, it literally just is going to go and it's going to time everything as it streams. That's it. Bob's your uncle. Okay. What we're going to do is first point at our bits and bytes endpoint, which we have manually toggled, right? Manually toggled to be bits and bytes when we created the endpoint, and then we time it. And you see it takes 2 minutes to get through 100 responses. We get an average request time of 1.4 seconds, 0.31 seconds time to first token, 13.86 tokens per second. Man, I'm not loving these numbers, right? And then average inter-token latency is going to be 0.06, which is not fast enough. There you go. Okay. So then that's bits and bytes. The thing about bits and bytes is, right, it is a ad hoc quantization strategy. All we have to do is say, let's do bits and bytes, and then we're doing bits and bytes, okay? There is no training step necessary for B&B. There is no way to do this. We'll look at the other methods, but the idea is that you can just plug bits and bytes in wherever. So it's great, but it's not very fast. It's not super fast. And this is after Tim Detmers has released custom kernels for it. Still not that fast. So GPTQ, well, what's different about GPTQ? Greg talked about it. You'll notice, though, that GPTQ and AWQ both, they have to train the model, right, in order to quantize. So the quantization is not like it's not just a thing that you can do for free. You just click a button and boom, it's quantized. This is actually a process that we do through training, right? So, and we're going to look at how we would do that in the notebook, though I'm going to recommend you to skip that section because it will make you pull your hair out a little bit because it takes a very long time. But the idea is that we have to train the model, right? And the reason we have to do this is because we're going to actually learn which weights are more or less important, right? Because when we say GPTQ 4-bit, like let's look at our inference endpoints, right? When we're looking at our GPTQ int 4, well, it's kind of true, but it's not 100% true because it's going to try to make as many weights as possible get down to 4-bit, right? But we're not going to be able to, we're going to have this kind of introduced parameter noise during the process, which we're going to continually update as we move through, as Greg explained, so that we're ultra quantizing the least important weights, and we're leaving the most important weights all Gucci. Okay. Then we're going to use, we're going to run this thing, and you'll see that we snapped. Okay, so let's refresh the page. Boom, we're back. And you'll see that we have 0.67, request time. It's better. We'll have a chart so we can look at this all at once, but it's better. 0.28 seconds time to first token, and then 28 tokens per second, and 0.02 intertoken latency. That's doing a lot better. Okay. Then AWQ, again, same thing, in practice. Most weights don't matter. This is the logic. This is the truth of the LLM. And it's counterintuitive, but almost every weight is useless in the LLM, right? It's an 8 billion, large pile of largely useless space. And so what we can do is we can hyper quantize everything that isn't the stuff that matters. And this is what we do with AWQ. Again, we get numbers that you're going to see look similar. We're going to graph this thing using Plotly, and you can see the numbers. Time to first token. In this case, higher is worse. So AWQ and GPTQ, very, very same. And then we have bits and bytes ever so slightly slower, right? Then we have our total generation time, bits and bytes, gets owned, absolutely owned by AWQ and GPTQ. You'll notice that something else about AWQ and GPTQ, they're like kind of the same, right? They feel kind of the same, and it makes sense. If we have the same LLM and we have the same exact philosophy, which is that most weights are useless, let's quantize most weights and let's only leave weights that matter as useful, then they should come to the same conclusion if they are good methods, and indeed they do. Tokens per second, lower is worse here, so bits and bytes again gets absolutely crushed, less than half. Oof, feels bad, but very flexible. That's why. And then intertoken latency, it's not even close. This is basically travel time between us and the endpoint, right? That's how fast it's generating. Okay. Your question, describe the difference between the performance profiles. Then we have checkpoint conversion. This says optional. I'm going to upgrade it to please don't attempt this in your breakout rooms. You will have a bad time. You should do this locally or in an environment where we have more control over the installs. The process to move NumPy to the correct version is going to be painful. And so we're just going to say, just don't bother with this in class today. But it exists if you wish to go through it. And basically what this does is it takes you through how we would convert a non-AWQ or GPTQ checkpoint into one of those checkpoints. So we have the AWQ instance. We can load the model, then we can do the thing. It takes 16 minutes, so 17 minutes just about technically to do this. And this is not including loading the model time, right? So 17 minutes to quantize this model. But, right, 17 minutes once when your throughput is very high, means that you're going to very quickly regain that time. Your users are going to feel that time And that's well worth it. And then the same thing with GPTQ. We have the process of how you would create a GPTQ model. And then, again, this process takes a very long time. You can see it's doing this layer thing that Greg was talking about, right? We go through all these sweet layers. We get a final model. You can see that the model, we saved 64% of the model through this quantization strategy. That's huge, amazing. And then, of course, we can do inference with it, and it inference very fast. I'm going to very quickly show you the VPTQ notebook, which I'll paste as a link in the chat. This isn't like what we're focusing on today, but it is dope. And this notebook runs all these models on the GPU in the notebook, making it slightly different. So there's no inference endpoints here. It's going to actually run in the Colab environment. So your mileage may vary depending on the GPU you select, depending on if you're running this locally or in the Colab, whatever it may be. But the idea is it's same. We have this information. We have VPTQ. We use this vector strategy. Vector strategy is interesting because it lets us consider things all at once. And then we do these little chunkies of the vectors. But it's exactly the same idea, right? Most weights aren't useful. Most weights are like whatever the mean is, right? That's it. They just sit around the mean. Very few weights are outliers. So same. The vector strategy is more complex. It increases computational complexity, not as in it takes more time, but as in it's harder to compute. But the idea is that we can run this test, and we'll just skip to the part where we see the pretty graph. And the pretty graph shows us that VPTQ in blue here has a little bit better time to first token. And then the total generation time is lower. The tokens per second is higher. And then the mean inter-token latency is lower. Now, again, this is going to vary wildly based on your hardware. If you do this on, say, like an A100 versus an L4 or a T4 or an H100, this is going to be extraordinarily different because we're relying on some specialized kernels for some of this VPTQ that are not supported or not well supported, depending on the generation of GPU you use. But the idea is when VPTQ works and you take the time to make it work, it can be very fast. So it might not be super popular these days, but it's worth effort compared to AWQ and GPTQ if you're willing to spend that effort and right size and select the correct hardware. But we're not going to talk about too much outside of that. For now, you guys will work through this notebook, benchmark the three methods against each other, look at this chart that you see here, right? And talk about how you think that performance is impacted with that question. That's the breakout room. I'm going to pass you guys back to, I think, Greg for a break, and then we'll get into breakies. Yes.
That's right. Quick break before breakies, guys. 5-minute break it out, shake it out, just for you, Dirk, just for you. 5 minute, and then we'll just hang and chat if you guys want to chat about it. So for those of you async that just missed this soliloquy from Wiz here, the long and the short of it is AWQ, GPTQ, these types of methods are for when you're ready to lock that model down, where you can use bits and bytes in a more flexible way. You can still do training and fine tuning. And as we learned, that's kind of how QLoRa actually works, the quantization and dequantization. So very cool. Remember, it's just rounding, bro. And we want to go and we want to basically compare inference across TTFT, ITL, TPS using GPTQ and AWQ. And don't say that to anybody else outside of AI Makerspace because they won't know what the heck you're talking about. But that's the kind of stuff that you're going to be walking away with. This does not have to be in your demo day presentation. Enjoy the next 25 minutes. We're going to sort of wrap in a flourish today. I'll remind you guys where you can get all the support for demo day. I will personally be available to help workshop your stories and get them dialed in. I'm really, really excited to see what happens next week. But enjoy your very last breakout room together working on an assignment as a journey group. 25 minutes. We'll see you back. Hope that you guys had a great time in breakout rooms, talking about quantization, talking about leading techniques out from the LLM edge. We saw a lot of them today. We saw quantization techniques, including GPTQ, AWQ, and we even talked about VPTQ in that extreme quantization regime. We really want to kind of just make sure that we're optimizing inference at the end of the day. We want to make sure we got that that performance, while also now starting to focus as we get into production on making things more efficient, run faster, and be more scalable in a cost-effective way to many, many users. Okay, so now let's talk about demo day. We've already talked about this. You guys already know enough. You know what you need to do. You know what you need to do to get your certification. You just got to finish demo day. Again, the homeworks this week are extra credit homeworks. You can get extra credit if you'd like. If you have specific concerns about your standing in the course, please reach out to Jacob, grading at AM Makerspace, to Sriracha, or to me directly, and we will get you ironed out, okay? We want you to focus on what matters most now, and we want you to really, at the end of the day, we want you to achieve your goals after the course in 2025 and beyond. We want to set you up for success. So if you need a little extra support this week, we totally understand. Now, for demo day, we'll remind you this on Tuesday. Be on time far in advance. We're going to do AVL check, audio, video, lighting. We talked about this before. You guys will screw this up on Tuesday because we're not going to do the check. We want you to suffer through screwing it up. So on Tuesday, we want you to do dress rehearsal, okay? Come dressed. Put your hat on. Make sure you're good to go. Plan to wear what you are going to wear. Get everything the same so you can sit right down into it on Thursday and feel like you've got experience. This is the point of rehearsal. We want all of your project ready enough to present, okay? Don't show up without a slide deck. It just looks bad, okay? Don't show us a bunch of code. We talked about this before. Show us a demo. Pitch the demo. If you're short on time, that's fine. You can always add more time. You'll receive feedback from peer supporters and from your peers. We want you to give feedback more than you receive it too. That's what we ask. Give first. We'll talk about this more on Tuesday, but when we start demo day, we're going to start on time, and we need you guys to be dialed in and ready to rock and roll. Graduation, we'll have a short ceremony following demo day. You're all invited. Bring your favorite beverage, whether it's alcoholic or not, no problem. And we will celebrate your accomplishment and your achievement together. Again, some reminders. If you need to buy a mic, go buy a mic, all right? Close the door, birds are chirping. Trust me on that one this week. AVL, video lighting. Make sure you've got, don't do like this. Don't do like this. Hey guys, hey. You want to get it squared in the middle. You want to get it ready. You want to know where those set points are. Speaking of set points, you want your physical space ready to rock and roll. When you demo, zoom in, guys. Zoom in, zoom in, zoom in. If you do nothing else, that's enough. Okay? Here's what we've learned in the past. We've learned people don't like the slides. There's too much clicking around. If you try to live demo and don't have a backup, you might have a bad time. Try to teach the audience something and open it. Open it with a story. Take me on a journey, okay? And slow down. And don't forget, share. Start sharing now. Start sharing like Mike C. Start sharing like Todd LLM. And remember, start being a community member this week, because as you graduate, you off-ramp from the cohort into the world and into a very valued member of our community. We've got interesting new initiatives in store that we're excited to tell you about next week, but focus for this week on building. Last minute alert, we've got some support on Saturday as well. Very first thing in the morning, PT, 10 a.m. ET. Kat is going to be there to support you guys around the world. So we do have coverage every day of the week, but still most of that day is going to be wide open. A great day for you to chill in the lounge and get with community. Now, if you're struggling with a bottleneck right now, don't hesitate to throw it into the AIE5 general channel. Don't hesitate to reach out to your peer support leads. We will share the run of show with you following class in the follow-up email, AIE5 run of show. And we will send out the run of show as well as the invite to over 10,000 people this weekend. Please let us know what you thought about today's class. I'll do a brief curriculum wrap on Tuesday to remind you everywhere we've been. And then we'll get right into rehearsals. And it should be a lot of fun. So it should be relaxed as long as you've got the stuff done. And come ready to listen as much as you are ready to present on Tuesday. Feedback 2 minutes. I'm going to steal 2 minutes from you today, but we're going to give you a lot of minutes in the coming weeks. Notice I am available on Tuesday. I'm going to give you guys 2 hours. If you want to come, you want to workshop the story with me, you want to really get those slides together, I could whip up a slide deck in 10 minutes from zero. I'm not saying you should come and rely on that, but I'm saying if you end up in a pinch, Wiz and I know how to help in a pinch. We do it all the time. All right, feedback, 2 minutes. Thank you. Let us know what you thought. Turn off those endpoints, everybody. And thank you so much for the feedback. Thank you so much for joining us for session number 18. We have been on a very long journey together through many weeks of learning. You guys are literally as much of an expert at building, shipping, and sharing production-grade LLM applications as the tiniest fraction of humans on the planet. Please use your power for good. We look forward to seeing what you build, ship, and share for rehearsals and for demo day. Join anyone who's here to support you guys over the course of Hack Week. Start acting like a real community member. I'll see you in the lounge on Monday, maybe every Monday, starting from here. There's lots more stuff in store for AI Makerspace and for the future, and for each of you guys and for each of your futures. We will see you on Tuesday. Have a fantastic weekend in the meantime, and thank you for all of your hard work over the last 9 weeks. We look forward to giving you a platform and a stage to show it off next week. And turn off those endpoints. All right, guys, thanks so much. We'll see you guys on Tuesday or in office hours and on Discord. Tag at AI Makerspace. Repost, like, and subscribe. With love, we out. Thank you, guys. See you on Tuesday. Tuesday. Let's roll.
Bye, everyone.
Later,
Bye, thank you.
everybody.
I know, Ashwin, you had a question,
Yeah.
so feel free to stick around for a minute.
Oh, Ashwin. Okay, what you got?
Wait, I want to be
You
a
gonna play you off, Ashwin?
I want to do one.
Yeah, Ashwin. Ashwin, what are you gonna spit some rhymes for us right now? What's going on?
Oh, can I ask or wait? I was not sure.
Yeah,
Seriously.
come on.
So nothing, Greg. It's more on the demo day thing. That's on that Thursday. I came to know yesterday that there's a math kangaroo exam for my kid. So I'm also managing it. So I will be most probably available later. So can you move me to later time?
Yes.
And I'll
yes.
try to come back soon, but it's like I'm managing there. So I need to go
You know
get
what?
the exam
If
done.
you promise me a banger, Ashwin, I can make you a closer. Okay. But I need you
I'm
to show
hoping.
up exactly the way you're showing up right now. Okay. In straight banger mode. All right.
Okay, now let me make it more realistic.
Yeah. Exactly. Make it more realistic. Even more of a banger. Okay. And yeah, let's put you in the closing spot,
Yeah.
but
But
you have to be there.
Yeah, I'm trying my best because the problem is that, yeah, there's an exam happening and I'm managing that whole center. So the exam is at 3 p.m.
Yeah.
and it's for 75 minutes. So
Okay.
I'm
Well,
gonna run tight, but 5 p.m. is when I'm going to shut it down and come. But that's my only.
shut it down at 5
I
p.m. Yeah,
forgot that
yeah,
there's an exam. I thought everything is great, and yesterday my daughter was like, right, next week is my exam. I'm like, what exam? Then I realized, oh, it's
Ah,
it's there, man.
the things we do for our kids. Am I right? Okay. Yeah. No problem. We'll work with you. We'll put you in the closing spot, and
Sure,
then
sure,
if you have any sort of last minute concerns, just communicate it with us as soon as you know.
sure. Yeah. Thanks
So
a
we
lot.
can
That's all.
adapt. All right. You bet, man. See you soon.
Bye.
Later, Dirk.
Later, guys. Bye.